Well, let's begin. I hope you recognize that music, which is Beethoven's Ninth Symphony, the choral symphony, which is, wow, my voice is strong today, I consider that sort of the anthem of the human race. Ode to Joy. Don't be sad. This is even though it's exam time. Nicht diese Töne, not these sad sounds. But the reason I play that is that we're going to touch today, I hope we get to it, one of the other great moments in human knowledge and greatness. That is the Maxwell equations, which are on I don't know if they're on a par with that for the world. Most people can recognize the Beethoven, but they won't tell you what Maxwell's equations are. I hope you will keep them in your heart from here on out, because they are the equations of electricity and magnetism, which govern so much of what our lives entail. The very fact that we're here is because of electricity and magnetism. But I wanted to start with something a little bit more mundane, and that is simply I didn't want to leave you with the impression that alternating current, which is what the power company provides, is all there is in our world. We start out, most of our energy comes from the power company, and it's alternating. As I mentioned to you, we have this what's called AC. That's not very good. AC, which means alternating current, actually they provide an alternating voltage, and you determine how much current you take. But depending on what resistance you put across their 120 volts of alternating current. So alternating voltage. This should be really AV, truth be told, but let's not quibble. Because the amount of current that you get depends. If you put on two appliances, you'll get current through both appliances, and you'll vary the current. So the alternating voltage is what they provide. You determine how much current you take, and how much power you use, and how much energy you use. Okay? But the thing is that our much of the appliance, some of the modern equipment that we use likes to see not alternating.
Just a quick question.
Yes, sir.
Are there just two different symbols for a battery? The one that you just...
Yeah, I will use that if I mean an alternating, sort of a generator, a wiggly thing indicating a sine wave, whereas a battery I would do is more static. What? I'm not sure if it's that.
Is that for direct current, or is it just...
I would even use it for all direct current, yeah. Because all direct currents are basically big batteries or something, but static. You know, they have a constant output voltage, whereas this fellow here is the voltage is going something like an amplitude. The V is some amplitude, and some sinusoidal thing, sine omega t. So that's what the power company is giving us. And I think you saw it when I generated, and I showed you on the oscilloscope. There were blips and so on. That's what the power company is. That generator was a little bit funny. It was only giving us one-sided things for some reason. I don't know exactly. We'd have to check exactly what the mechanism there was. In any case, it's an alternating thing. It's not what you get out of a battery, steady voltage. But, as I'm trying to say, you're very familiar with these kind of adapters, because what the modern equipment wants, like a computer, it doesn't want AC. It wants direct voltages, steady voltages, and relatively small, because these electronic components are made of semiconductors, and all they need is like 10 volts direct. So your battery in here is around a 10-volt battery. Problem is, of course, that the battery discharges, and you have to recharge the battery, have a rechargeable battery in here. But you need around 10 volts. So how do you get 10 volts DC out of 120 volts AC? That's what I just want to say a couple of words about that, because you use it all the time, and it's good for you to know. Well, what you use is these little adapters, right? You plug this into the wall, so you get your 120 volts across here, AC. But out of here, this wire comes DC, around 10 volts. So how do they do that? Oh, it's it's simple, but relatively simple. Let me see. I even have a, let's see. Yeah, so what you see on the left there is your AC power line. That's your 120 volts coming in to a transformer. Because you see, starting with 120 volts, you want to get down to around 10 already. At least 10 and DC, but at least get down lower to 10 volts. So you step down the 120 volts by putting, well, they didn't draw it very well there. There should have been more turns on the left than on the right. Right, folks? Is there no, what's happened? Huh, what's going on here? Screen, oh my goodness. Sorry, folks. Sorry, you tell me these things. Yeah, this diagram is a little inaccurate. I think it comes out of the book, but nevertheless. So what he should have showed is that if you have your alternating coming out, you want to step down. So what do you do with the turns on the different sides of this transformer? You're trying to get less voltage, maybe more current, but less voltage, because you're trying to go from 120 to 10, or say 12 to make it easy. So what turn ratio would you put in here? Anybody? To go from 120 to say 12? Huh? 1 to 10, yeah. So I would put 10 turns here. I don't know if that's 10, but there. And I'd put 1 turn here. So if I come in with 120 volts, I'm going to come out here with, if this is 10 to 1, I'm going to come out 12 volts across here. But now I've got 12 volts AC. Oh, I'm getting there. But the thing is that what's coming out here is wiggly, and I don't want that. I just want 10 steady volts. I want 10. Oh, if this is 0, and this is my volt, I want, because my computer wants 10 steady volts. So there is a device which will do the following thing. When you put it through this device, and it will only let the current pass on one side. So it'll do something like this. It's called a rectifier. Rectify means to make right. Well, in a way, it makes it sort of right. And so now at least we've got at least one sign, right? So that's already good. Then we have to smooth it out, because you really want this. So you put in, how does it show that? A capacitor. Well, there really should be a capacitor in there to slow it, to smooth it out. Because a capacitor holds a charge, and so then you'll get something like this. And if you do it well enough, you sort of end up with maybe a little bit of ripple. But you see how by suitable electronics, you can convert AC to DC. And actually, if you go home and you look at your thing, it will say on it, like mine over here says, 120 volts, 60 hertz, so it's 60 cycles, 12 watts. So you can put 12 watts into this or out of it. And output, 7.5 VDC, 7.5 volts DC, 500 milliamps. If you look on each of you, and all of them are different. I have another one here. Do you collect these like I do? I mean, things go out of style, and you end up with all these adapters. This one is 120 volts in, 60 hertz, so it's for American current, 18 watts, 9 volts DC, and 600 milliamps. So you could look, and you'll understand these things. which you're using all the time. I'm sure. Yes? Any questions about that? Just passing reference to that because it is very interesting that we use, and you can go the other way too. If you have DC, you can convert it into AC if you need it. For example, that happens in the old cameras where you want a high voltage to make the flash, but you only have like a 1.5 volt battery, DC. So what are you going to do there? There you have the opposite problem. Okay, well, let's even use this diagram because we can... Oh, no, I have to start on this side of the diagram. So I start out, in this case, with, say, a 1.5 volt battery, DC. And I'm trying to get a high voltage to flash my camera. But it's certainly not going to flash with 1.5 volts. So it's going to be a little bit like the experiment I did with the auto spark plug thingy, where what you want to do is you take this and you can actually interrupt this DC. See, if you have the DC like this, you can get a device which will interrupt it. And so you're getting kind of an AC here, and then you can put that through a step-up transformer. So you do something like this. You put it through a step-up transformer, and you build up a big voltage here, and then you might want to rectify this and get, say, so if I started with 1.5 volts and I go 10 times, I would at least have 15 volts. But if I put, 1,000 turns here, might get 1,500 volts finally. So you can go from DC to AC, back to DC, and get what you need. And it's done all the time, behind the scenes of what you're doing, right? Does that sound like fun? No. Okay. The other thing I wanted to talk about, here's this AC story. Very modest on AC. All I want you to know is that it exists, that when we speak about 120 volts, it's sort of the average, the RMS value, that there's a peak voltage which is higher, and so on. That's good enough, and that the key thing is knowing about transformers because they're a big part of our both electric generation, transmission, and even in little devices like that, there's a transformer in there, a lot of other places. Now, this story, I don't know if we have time for, it's nice, but what I do want you to learn about is this. It's the returning to a story we had with electric things, where we pointed out that you have different kinds of materials. Maybe I could run ahead to another slide to remind you of this one. See, on the left side, these are things we talked about before, properties of materials. And on the electric side, we have what was called a dielectric material, paraelectric material, and a ferroelectric material. What they were was the dielectric is everything. Because what it is it's an atom put in an electric field, and the electric field, the external electric field, polarizes the atom or molecule by making the negative charge move one direction, the positive perhaps move the other, stretching it out, creating a dipole in every material in there. That's a relatively weak effect usually because, again, in materials, these electrons are very much attached. They're sort of like married couples. They're very much attached to each other. And this external field just stretches the thing a little bit, but not necessarily very much. And it ended up actually having the effect, we saw it when we had a capacitor and you fill it with different materials. And we said that there was a kappa dielectric constant which represents this polarization effect. And typically in dielectrics, the numbers were if you look back on it, in the order of 3, maybe 5, maybe something like that. It's less than 10. Typical effect due to this, namely that the charge on this capacitor, the capacity would be kappa epsilon naught area over D for a parallel plate capacitor. The charge on the capacitor, or the capacity itself, would go up by this factor of kappa. In a dielectric, this is maybe 3. The reason being, again, that you created a minus and plus on in the material by putting a field on it, which invites more charge to be delivered from your battery. So you get a delta Q, which could be a factor of 3, which is not bad. So there's more charge by the factor of 3, because this, you remember the capacity is Q over V, Q over V. So the fact that for a given voltage you get a bigger capacity means that this capacitor is actually holding more charge. Right? I hope you remember all that. This is, fair game on the exam, so eyes pop open. So that's a dielectric, and that's the physics behind it. And what you get is more charge delivered because the polarized material invites more charge to get on the capacitor. Now, we have the other case in the case of electric materials, the para-electric case, where what we had was molecules with built-in dipoles. For example, the famous water, where you have your dipole like that. And that's built into the molecule. So when you put that in an electric field, like you put it in a capacitor, all those dipoles are going to try to line up with the field. Something like that. Right? Now, because these things are pretty big dipoles to begin with, this is an atomic distance. The other was a fraction of an atom distance. The polarization of something like that, sort of like a fraction of an atom. This is a whole atom, D. The distance here is sort of atomic scale. So that's already a big factor. And in fact, you find that if you put water in here, you'll get a capacity, the kappa epsilon naught A over D. Kappa can be, for the case of water, I showed you 80. It is 80. It's 10 times more than a simple dielectric. And that's the reason. It's because there are these already big molecules with their big dipoles in them. And then, of course, the third case is the ferroelectric, which by analogy we'll get to ferromagnets today, I hope, where the electric dipoles are structurally organized, spontaneously organized, so that all your dipoles are organized even in the absence of a field. So here you've had to put on a field to get these things to line up. Here the thing is spontaneously organized. And so even without a field, you'll get electric field coming out of this thing. Where here you won't. Here they're just randomly wandering around, but they're waiting to be polarized, but spontaneously not. Here you get a spontaneous electric field coming out. The special materials, these titanates, for example, barium titanate, strontium titanate, others like that. And because of this well-organized thing, if you put those in a capacitor, you're going to get your kappa in the order of hundreds, the order of 300. I think I gave you a table showing that. And this is the physics behind it. It's relatively straightforward, right? Yes, sir? Dielectrics are particularly... The question is... Pardon? He's saying that in the book it says the dielectrics used are typically metals. I would say, I doubt if the book says that because it would not be true. The point is you wouldn't want to put a metal between it. If you do, you don't have it. It's not a capacitor anymore. It's a metal. The charge would not stop here. See, the thing about a capacitor is the charge stops at the top and it's collected to the bottom, and it can't get through. Unless, well, somebody once brought you could raise the voltage high enough, you break it down. That's another story. But no, you do not want it to be a metal. And I said that I think that it would not, to me, it's reasonable to say that a metal could act like a dielectric in the sense that it's polarizable. If you put a chunk of conductor in an electric field, it will polarize. So in that sense, it's a dielectric, and it fulfills the criteria. So if it fulfills the criteria that it has no intrinsic dipoles, it's not spontaneously polar, and the charges move under an electric field to produce a polarization. So in that sense, it is a dielectric, but it's not an insulator. What you need in a capacitor is a dielectric and insulate in a capacitor, because you don't want the current to flow from the plus to the minus plate directly. So in a capacitor, you want that, but this is maybe a contentious point, but in a way, a conductor is dielectric in the sense that it has polarization properties even larger than an insulator, but it's not a good, it would not put it in a capacitor, because you would change, it would not be a capacitor anymore. The current would just simply flow from. It's a good point. I'm glad you brought it up. I don't think you'll hear what I just said see it in books, but logically, I would consider this a dielectric in the sense that it's polarizable and doesn't have any spontaneous and all that stuff, but it's not an insulator. So there should be a distinction between an insulator and a dielectric. Dielectric just means it's polarizable, as far as I'm concerned. So I think there was a book that said Captain Queeg in Caine Mutiny. He said, the captain of the ship said, there's the right way, the wrong way, the Navy way, and my way. Here we do it my way. So I guess for this course, do it my way, and we'll all be happy. Don't tell anybody, though. Okay, so this is a review of the materials, classes of polarization properties of materials. The same pattern exists in magnetic materials. That's the gist of what I'm going to tell you. Let me go back to a couple of things. Now, this is good material for, well, let's see. If I can leave something on the board. You see, the point is that what you did in a electric case, you had a material, you put it in an electric field, and you let me make the analogy a little bit simpler. Let me have a material here, and I bring, this is the first experiment we actually did, where you have a styrofoam ball and you have, say, another styrofoam ball, and you charge up one of these balls such that you have an electric field coming out of it, okay? And this is, say, an uncharged ball. How does the uncharged ball react to the charged one? Well, by dielectric, it polarizes. You stretch the molecules such that you start to pull the minuses a little bit toward this one, and the pluses are left behind, actually, and so you end up with a polarization. And because the minuses are now closer to the pluses, there's a net force attracting these two together. I think we demonstrated that first day. Okay, so that's dielectric polarization, and it leads to an attraction. Let's see what would happen if you did the same thing with magnetic something. Suppose you had a material here, and you bring toward it a magnet, let's say North Pole. And I'm bringing this North Pole toward this material. This material has electrons in it that are attached to atoms, so they kind of at least can wander around the atom. But what I'm doing here, I'm making a changing magnetic flux in this material, which by Faraday's law will create an EMF or an electric field such as to oppose the changing magnetic flux that I'm bringing toward it, right? So I have a dB this way, a delta B, and by my right-hand rule, I'm going to create a delta B the other way. Or maybe you can call it a little b. And a delta B in that direction is caused by currents going out and around. Again, it's hard to draw. Can you see? It's going to be a loop of current coming out of the blackboard, going in that direction. In other words, that opposing induced magnetic field will be a north pole, because the current is coming around, the induced current is coming this way, and I'm creating a north pole in the material. You see that? It's an interesting point. Think about it. Because I'm bringing a B here, I have to create a B opposing the oncoming B. And that means I have to have a current going here. But the fact that it's an oncoming B, that makes it a north pole here. So you've created a north pole in this material, which is it's going to oppose the approaching north pole. So oddly enough, this is called the diamagnetic because it happens in everything. Everything has electrons, everything has nuclei. So it's diamagnetic, just like this was dielectric. But the interesting thing is that it's repulsive. The material's if you bring a material close to a magnet, the force will be opposite to getting closer. So the force in a diamagnetic case is repulsive. There is a story that you could take a frog and put it over a magnet, and if you drop the frog, because you induce currents in the frog, it'll float. So I've heard that story. I've never tried it. I have to catch a frog, which may be the hardest part of the experiment. And apparently it can float. In fact, people are thinking of making diamagnetic. If you can make the diamagnetic bigger, it's like a suspension possibility. They're talking about making trains, for example. If you could make the train suspend, you see, you're not even doing anything. All you have is a strong magnet below. The thing above is suspended just because as it gets closer, there's a repulsive force which keeps it up. So in a way, you don't even have to do any work. Yes, sir? I'm thinking of it coming out of the blackboard. Let me see if I can draw it better. That may be clockwise, but it's coming out of the blackboard and going into the blackboard this way. It's hard to draw, isn't it? I might even have. I brought this. I don't know if this makes any. You're going to have current coming this way in order that the magnetic field coming out of that loop be downward. Can you see that? Now, I should have brought this. Right? Yeah. So you see where there's a north pole coming out of here? Because that's the way we define the north pole, is where the field's coming out. So you're creating a north pole when you bring a north pole toward the material. I don't know how to describe whether that's clockwise or anti-clockwise, but that's what it is. You got that? Okay. That's great. And there are people who are trying to get the diamagnet. If you can get the diamagnetism high enough, you can expect to float things, actually suspend things. Now, we also have the analog of the paramagnet. This is the diamagnet. We have the analog of the paraelectric, which is called paramagnetic. Surprise. I mean, so we have the paramagnet. What is that? It means that there are built-in magnetic moments, one of which is the hydrogen nucleus. When you do nuclear magnetic resonance, the nuclei of the hydrogen have their own magnetic moment. And they're far apart. They're on different water molecules, say, or your other organic materials, whatever. And they're all, the magnetic moment can point any which way, up and down. So you have it's the analog of this. Also, you could have the electrons in a conductor. They also, electrons are, the reason they have magnetic moments is because they're charged and they have spin. So it's a current going around an axis like this, perpetual motion, perpetually going around. Built into the nature of a proton is that its charge is spinning around like that. The whole object is spinning, and since it's charged, it's a current, and it's producing a magnetic moment. And that's true also of electrons. It's true also of things like ions. They have magnetic moments. So if you have an iron impurity in a material, it'll have a magnetic moment. And if they're not coupled well to each other, they'll just be pointing any which way, sort of like these. But if you put them in a magnetic field, they'll try to orient. They'll turn parallel to the field, if they can, as much as they can, and the thermal motion will jiggle them. And we call that a paramagnet. Very common, and when you do nuclear magnetic resonance, what you're doing is nuclear paramagnetic resonance. Paramagnet. When you do it. Now, when I've done it also, but you can also go to the next stage, which is ferromagnets, the guys that you first came across as a child. Ferromagnet, and here's where the word ferromagnet comes from. Ferro, of course, because the first magnets that were noticed actually had iron in them. So the whole class got that name, although you don't have to have iron in it. And what that is that you have magnetic entities in a block, and they spontaneously organize in what's called domains. And they give you a big spontaneous field, even in the absence of a field, even if there's no external field, they, as you well know, as we've done compass needles and all that, they spontaneously put out magnetic field. They're organized. Now, if you do put them in a magnetic field, what happens is that sometimes the domains, typically the domains are small but noticeable. If you put in a magnetic field, what happens is the domains rotate again to align with the magnetic field, and so you get yet a bigger effect. So that's one way of getting a big magnet, is by putting a ferromagnet in a magnetic field. And here, again, you get a big change. Let me see if I have numbers here somewhere. So here are the different kinds. You have the diamagnetic, paramagnetic, ferromagnetic. Here's that chart again. And to give you an idea of the magnitudes, I repeat that chart. If you put these electric materials in a capacitor, they will charge up. They'll give you more charge depending on what material you put in. You see the first group there on the left are things like polystyrene, paper, and so on. The numbers like 3, 4, 5, 6 over there. Okay, but then if you get down to water, you get 80 times as much charge on the capacitor because of the the para-electric. And then if you put in strontium titanate, you get 300. That's the biggie. That's the permanently magnetized. Now, the same thing is true if you take a magnetic material and you put it in big inductor like that, we'll see in a moment, the diamagnetic minus. In other words, it's not aiding, it's opposing. You get this opposing repulsion. So you see the diamagnetic counterpart is minus, but very small, 10 to the minus 6. Because all you're doing is you're making the atomic electrons rotate in such a way that they're opposing the oncoming field. It doesn't have to. The trick for people who want to apply this is to get that number higher. But a simple thing like water, the diamagnetic constant is small but negative. Then if you have a paramagnet, it's a lot larger but positive, because there you're lining up the dipoles and they're helping you. And for a ferromagnet, it's whoppingly big, thousands. You can get 1,000-fold increase in the thing, because what you're doing is taking a thing that's already well magnetized, just lining it up, and you get a big field coming out. So you should know about that. Now, if in your life you come across, the diamagnetism depends on currents going around an atom. These flat molecules can give you quite a big diamagnetism, because the orbit gets big. And you remember the magnetic moment is the current times the area. So if you can get I've actually looked for this to see if you can get it big enough so that it can become practical. If you can get a big orbit and delocalized, you might get a big enough diamagnetism to actually do something useful, like suspend things. That you put them down over that stuff and put a magnet over this stuff, and the stuff will be suspended, because you'll get a big current with a big loop area. The other thing about these permanent magnets is that, and this is an interesting point, true also about ferroelectrics, is that if you raise the temperature high enough, the thermal agitation will sort of break up this ordered of the magnets. The material itself may not melt, but the order of the magnets may melt, and it turns in at a certain temperature, the order in the magnets fades away, and the ferromagnet becomes then a paramagnet. You don't lose the intrinsic magnetism of the atoms or electrons, but they're no longer self-organized. And that temperature is called the Curie temperature. This is named after actually Marie Curie's husband, who worked in magnetism until he and his wife switched over to radioactivity around 1890. He was a very good physicist, and when he got together, the field of radioactivity blossomed, and they jumped from magnetism to radioactivity, and of course did wonderful work there. But Curie's name is given to that. And so the Curie temperature for both ferroelectrics and ferromagnetics is, if you make it cool enough on a ferroelectric, it will spontaneously organize, like freeze in. And if you same with the magnet, if you make it cold enough, the magnets freeze together and make a nice strong magnet. You make the temperature too high and that magnetic order goes away. And so, putting all of that together, here's a slide which I just will leave with you, showing the different behaviors. The point being that in every one of these circuit elements, as I've mentioned a number of times, there is a materials factor, material, and then there's a geometrical factor. The material can either be rho, in the case of a resistor, kappa epsilon naught for the capacitor, and in the inductor, it's a mu zero. The mu is the kappa reflects whether it's a dielectric, paraelectric, ferroelectric. The mu represents whether it's a diamagnetic, paramagnetic, or ferromagnetic. Now, to show you the power of this a little bit, we only have a couple of minutes more. I wanted to also point out that in each of these cases, you have an energy issue. We pointed out that in the case of resistors, energy is dissipated. At a rate, the power, which is the energy per unit time, I squared R, or V times I, or V squared over R. But this is the energy dissipated. In the case of the capacitor, what you've done, after a period of time, the capacitor collects charge and stops when the imposed voltage is backed or opposed by the voltage you developed on the capacitor. And a certain amount of charge has arrived at the capacitor. That charge is the current that you put into the capacitor times the time, because current is charge per time. So over a period of time, the capacitor charges up, and then it sits there with a voltage on it. And then there's energy, let me call it U, inside the capacitor, stored in the electric field. And it's given by, again, this epsilon naught, we've been calling it kappa, epsilon naught, E squared over 2. There's energy stored in the field. I demonstrated that once by charging up a big capacitor, and we shorted the terminals, and we got the big flash as the energy discharged, because what I did was I put a short circuit over here. I brought a metal ball between the contacts here. And when I got close enough, the voltage here, well, I opened this first because that would be nasty. The voltage here causes the electricity to jump across, and I discharge with a bang. Likewise, you can have the same type of circuit. Typically, you'd put a resistor here across an inductance. What happens here is that at first, the inductance stops the current from going, but eventually the current, this becomes a short, and you get a current going through the inductor. And in a way, the inductor is getting charged up, not with electric charge, but with current. Because this is becoming a wire over a long period of time, the current in that, when you turn it on, goes up and stays at some value like this. So the inductor gets charged up with current, but the current is producing a magnetic field in here. So you have a magnetic field inside the inductor, and that also represents an energy. It's a magnetic field energy, and again, by these beautiful analogies between fields, electric and magnetic, the formula will be B squared over 2. And as I've said before, if there's an epsilon and k on top, there's typically a mu and a mu zero on the bottom. So you'll get the formula looks like mu over mu zero. So that's the energy stored in a magnetic field. That's the analogy. Now, to show you that, we have a couple of minutes. We're going to be evicted because of the colloquium in a couple of minutes. They will come. Here is a large inductor, and inside is a chunk of iron, which is a ferromagnet, and it's going to help boost up this total amount of magnetic field inside this thing. We have 6-volt batteries here in series, I was told, I guess. It doesn't matter. And it's going to send current. After a few minutes, the current will build up, and not a minute, seconds actually, it's very fast in this case. It's going to build up, and I'm going to get a lot of current flowing through the coils. So I'll have a strong magnetic field here that's been built up. Then when after I close it, but after I open it, all that magnetic energy is stored here. It's going to have to go someplace. So we have this little lamp, which will, the current that's, the EMF that's generated by the falling field will light the lamp. Now on the way up, charging this thing, the voltage is very small and the lamp does not light. Let's see if that's true. So on the way, I'm going to close it, send current into these coils, and in principle the lamp does not light while it's going up. So now the field is charged up. But if I release it, whoop, let me see. What happened? Foiled again, folks. What happened here? Oh, when all else fails, plug it in. Okay, folks. Perfect agreement with the experiment. Now let's see what happens. Can you see over? No, she's all by herself. I can't move any of these either. They're all nailed down for some reason. Okay, so now let's see what happens. If I put current in the coil, doesn't light, but see, when you dump all that energy out quickly, it generates a voltage here. Do it one more time. Yeah, I'm putting current in here. There's all loaded up with magnetic field, and then it dumps out here. Now, just for fun, I'm going to take the core out because I said that if you put a magnetic material in here, it boosts up the magnetic field. So let's see what happens if I should take this out and do the same thing, leaving the wires attached. Okay, so I'm charging up the current. So it's the same magnetic field as far as the coils are concerned, but there's no magnetic thing to help. Nada. In fact, they said if I turn out all the lights, can we do that? You might just see. I don't know. Let's see. But you see, it's a lot less. So I'll load up the thing with current, but there isn't much magnetism because the core is out. It did light. Could you see it? Very dim. You can't see. Yeah. So the effect is much, much improved if you do put in this magnetic thing. And so this is the mu that is in the inductance. So I'm loading it up. It gives you a faint glow, but bam, when that gets, then that big magnetic field gets changed and causes a voltage. Well, we didn't get to Maxwell, so maybe we'll hear Beethoven again next time. No harm in that. Anybody have? Oh, I meant to say, there were some questions about what's going to be on the exam. There are certain exclusions which I mentioned along the way. Exclusions including, I've said this many times, but section 24.2 and 24.5 are about the mechanisms of conduction. Don't worry about whether it's a semiconductor and this and that. All you have to do is know there's conductors and insulators. All you have to know. And this is the one on safety. It's good to be safe, but we don't have to read too much about it. Then the other one that you're not responsible for is 25.2. I think this is multiple loops, the so-called application of Kirchhoff's laws in all their glory. You don't need them in all their glory. All you need is parallel and series circuits. That yes. Sir? LR? No, it's RC you're allowed. No, RC, yeah. RC. That's a very good point. That's 25.5. These are capacitors, RC circuits, but not the math. Don't worry about whether it's an exponential and RC time constants and all that. But qualitatively, the way I described it just here, the physics of it, that, yes, you should know, because that's intrinsic. You don't have to know any math to know I'm building up charge. It takes time. And after a while, it's charged up, and then very short, it's charged down. Say it again louder. No, there'll be no fancy mathematics, integrals or fancy derivatives. It's good to know what a derivative dq dt is current. It's good to know that. There'll be some arithmetic, simple arithmetic. You don't need a calculator. You're not allowed to have a calculator in the room. No electronics. Don't try to bring anything. You don't need any paper, blue books, nothing. You're allowed one sheet. Oh, that's another point. One sheet of paper. There seems to be some confusion. I try to make it clear. One side of one sheet with notes. The next exam, you'll have the other side. The third exam, the final, you'll have 3 sheets. Okay, is that clear enough? See you. Oh, by the way, next Wednesday you can come or not. We'll bring your questions. I'll review whatever you want to talk about.